Hello everybody, welcome to our new lecture on learning paradigms. In the last lecture, we have already started discussing about pretext task based self-supervised learning. In this lecture, we will start discussing from the same pretext task based self-supervised learning, and then we'll move ahead to other techniques. So, talking about context prediction, the key idea here is to predict the relative position of image patches, and when doing this, enabling the model to understand object structures and scene layouts. So let us try to understand this in a bit more details. The first step in context prediction is patch extraction. That is, given an image, we can divide it into a number of patches or grids, right? Let's say 3x3 patches, or even 5x5 patches. It could be, of course, a different number as well. However, for sake of simplicity, let us just assume that we are talking about 3x3 patches. So in this case, we have a central patch, right? In the 3x3 patch, the central patch, and we can consider its neighboring patches. That is all the other patches except the central patch. How many of them are there? There are 8 such neighboring patches. So this results in a relationship or a context which we can formulate as a pretext task. How? Our task can be given the central patch itself and given one of the 8 neighboring patches. The task is to predict the position of the neighboring patch relative to the central patch. That is, we are tasking a CNN or a network to learn to classify into one of these 8 possible categories. So this is what we just described, represented in a bit more pictorial manner. We see that the image has been divided into 9 patches, and we see the central patch here marked as 0, and the 8 neighboring patches 1, 2, 3, 4, 5, 6, 7, 8. And considering that we are taking this central patch and one of this neighboring patch, the model's task is to classify into one of these 8 classes. Now, some questions that we would specifically like to ask with respect to earth observation. So here we emphasize that this task of context prediction, or most of the other self-supervised learning pretext tasks was proposed first in generic computer vision literature. And then some of them were reused in earth observation, some of them were not. So what decides whether we can use it in earth observation or not? One of the important questions in earth observation is, of course, the spatial resolution of images. So the first question that we are asking ourselves is, does such context prediction depend on the spatial resolution of images? Think of an image which has, let's say, 10 centimeter per pixel resolution or 50 centimeter per pixel resolution. In contrast, think of an image which has, let's say, 30 meter per pixel spatial resolution. In 30 meter per pixel spatial resolution, if you think carefully, such context relationship starts fading compared to when we talk about higher resolution such as 10 centimeter per pixel, 50 centimeter per pixel, or 1 meter per pixel, where, let's say, there is a building, there is a road next to it, such relationships are very strong. Whereas 30 meter per pixel, or even like if we go even coarser, let's say 100 meter per pixel, in such cases, we are considering in 1 pixel a significantly large block, and there the relationship with the next pixel becomes less prominent. I should emphasize relatively less prominent. So, depending on which spatial resolution we are working with, the context prediction can be more or less useful in the case of earth observation. Now, let us discuss a bit the case of rotation of images. We have already briefly mentioned about this particular pretext task when we were introducing the self-supervised learning itself, right? So, in this case also, the question that is important is how effective is rotation of images as a pretext task for earth observation images, or let us refine this question even a bit more. Let us ask ourselves, how effective is rotation of the images as a pretext task for the top view images? So think about the top view images and think, if you rotate such an image at 90-degree angle, 180-degree angle, or whichever other angle, do you see much difference? Or rather, the question is, are you now in a situation to guess, okay, this image was indeed 90-degree rotated or indeed 180-degree rotated, in comparison to front view images, where, like, let's say from the front view you take a picture of your of a person, and then you rotate this 90-degree, you will be easily able to say that, okay, this image seems to be rotated, right? However, when you are taking a top view image and rotate 90-degree, are you in a position to make this prediction? So think about this. The answer will be most of the cases no, right? And hence the effectiveness of rotation of images as a pretext task for top view images is quite limited. The next pretext task we would briefly like to discuss is image jigsaw puzzle. How does image jigsaw puzzle work? It works by again dividing the input image into a grid of patches and then shuffling these patches to create a new version of the image. Then the network is tasked to predict the original order of the patches, that is, for a particular shuffling or permutation order, you could assign an index, and the task could be to now predict whether this image belongs to this particular index or not. So here we have seen an example. Again, we see that the image has been divided into 9 grids, and now for a particular permutation order we assign a particular index. Similarly, we can take more number of permutation orders and we can accordingly assign some indices. Let's say we in total take 64 such permutation orders. Generally, we won't take all possible permutation orders because that number generally would be a large number. Now, the model would be asked to predict that, okay, this particular shuffled image indeed belongs to this class 64. So this is how it would generally work, where given each of these patches in the different order, we would be processing through weight shared CNNs. Now, let us recall that making the pretext task more challenging makes our self-supervised learning more effective. So you recall from our last lecture, we have discussed this particular plot where we said that if we could somehow plot in the x-axis, let's say the difficulty of the pretext task, and in the y-axis the effectiveness of self-supervised learning, you would see that initially the performance or the effectiveness of the self-supervised learning will improve with more difficult pretext task. Of course, you make the pretext task very, very difficult. That's a kind of, in other way, impossible to predict. Then the self-supervised learning effectiveness also drops. So now, thinking of that hypothesis, again, we would like to ask ourselves that, let's say, this particular task that we just discussed briefly right now, the image jigsaw puzzle, is there in a way that we can make it more challenging. So to make it more challenging in other way, we can say is equivalent to deliberately losing some information at the input stage, because if the input stage this has less information, the model would find it difficult to predict the particular index, right? So how can we possibly lose some information?
Before going to the next slide, maybe you can take a pause here and think for 5 seconds. What could be the possible mechanisms? Okay. So one
Very straightforward mechanism could be to grayscale some of the patches. What do I mean by grayscaling some of the patches? Let's say our input in this case is 3 channel. Different channels, they're carrying different information. However, instead of this 3 channel, if you feed just 1 channel, or let's say an average or a grayscale version of these 3 channels, then the model is getting less information for those patches, right? Similarly, there can be other ways also to make this task more difficult, however, not make so difficult that it becomes impossible to predict. So as we have already briefly touched upon, the pretext tasks like rotation, they are rarely used in Earth observation. Same for Jigsaw. Jigsaw, again, this depends on the spatial resolution. If the image has high spatial resolution, that is something like 10 centimeter, 50 centimeter per pixel, in that case, Jigsaw would be comparatively more effective compared to the case of 30 meter or 100 meter per pixel. So in summary, this depends on the spatial correlation. Now, we would take a couple of minutes to discuss a couple of pretext talks that were proposed more specifically in the context of Earth observation. One of them is geolocation classification. It often happens that the geolocation metadata is available with the geoimages. So what we can do is we can cluster the data set according to its lat long, and now we can train a model to predict these clusters. There is another pretext task in the computer vision literature called image colorization, where let's say there are particular channels of the image. So we are talking about LAB color space, but it could be, of course, in some other color space as well. In the LAB color space, let's say the input is L channel, and the output could be predicting the A and B channels. And this particular task can also be very easily used in the context of Earth observation by dropping a band from the image and tasking the model to predict this particular band, or even alternatively creating a synthetic band, let's say NDVI, normalized difference vegetation index, and now based on some particular inputs, asking the model to predict this NDVI value, let's say. This particular style has been adopted quite a lot more recently when training model for, let's say, synthetic aperture radar images. We will discuss more of this in more details later in our course. The idea is thus is to drop some bands and use rest of the bands to predict the missing band, or predict a particular transformation. Similarly, another idea is the image in painting, where the idea is to mask and then restore local salient regions. Think about this, whether it will be applicable to the aerial images. Think in the terms of resolution. I'm giving you hints. So think in terms of the resolution, how it relates to the resolution, how it relates to the discussion that we have already done in our course before, or rather in this class, today's class before. And interestingly enough, this image in painting idea also is a very important idea when you study about self-supervised learning in the era of the vision transformers, which we'll discuss later in this course. Let us take a moment to think about pretext task for video. In the computer vision, researchers work a lot with the video. What is video? Video consists of frames. The frames you can think of as individual image. Generally, these frames, this follows a order, right? Like the frame number 5 and the frame number 7 generally will be more related than frame number 5 and frame number 10, right? So, inspired from this, in the video domain, there have been more than one work, I will say, which use this property and roughly created pretext task. There are variations, but I'm talking about the main gist. Pretext task based on the idea that we shuffle the sequence of the frames and then we learn to rearrange back this shuffled sequence. Now, let us take a moment to think about what are the possible inputs or sensors in Earth observation that are somewhat like videos. Of course, one could take a aerial video itself. I'm not talking about that. I'm rather rather restricting myself to the more popular Earth observation tasks. So, one possible answer would be the time series images, irrespective of whichever sensor it's taken from, whether it's multispectral sensor or whether it's synthetic aperture radar sensor. The time series images, they also have multiple time instances like the video. One key difference, of course, is that most of the time in the video, each frame has been taken so close in time that you just don't see, one object was there in this particular frame and in the very next frame this is totally gone. However, depending on what is our temporal resolution in the time series images, this is quite possible, or pretty much it occurs also depending on the application. Like if we're talking about, let's say, urban monitoring, considering an earthquake happened, even if the time gap is just 5 days, it's quite possible that a lot of the buildings which were present today is not present in the next acquisition, right? Whereas, of course, if you're talking about agricultural monitoring, things can be slightly more gentle, I would say. Again, there are subcases even in the agricultural monitoring as well. However, still, the time series images to some extent follow the similar property as video, right? So, we can, for time series images, create pretext task where we ask the model by jumbling the temporal data in random order and then learning to rearrange. Or it could be even like different versions where like we jumble the temporal data and we try to give particular index for each of these shuffling and try and ask to predict this shuffling index. But the key idea is that jumble the temporal data and in some manner ask the model to reconstruct or give hints about this order of the jumbling or order of the shuffling. So what are the other possible input sensors in Earth observation data that are somewhat like video? We already talked about time series images. What about the hyperspectral images? At this point, I'm not talking anymore about time series, rather I'm talking about monotemporal image, that is single hyperspectral image. So the hyperspectral image, does it have somewhat similarity to the video? Think about this. In which way hyperspectral image can be similar to video? So the answer is more in the spectral domain. Hyperspectral image generally consists of hundreds of channels. And again, if you think about these channels, they follow a nice order where each band and its successive band would generally be related somewhat. So following this, what we could do is, given hyperspectral input, we could shuffle the bands of the hyperspectral image. And then on the top of this, we can create a number of pretext tasks. One possible very easy pretext task could be to just predict whether the bands are shuffled or not. However, of course, again, more challenging or different questions can be asked, like asking to shuffle back or given an index for a particular shuffling order and asking to predict this particular index. Okay, so far in this lecture, we discussed about a number of pretext talks, both from the computer vision domain, their applicability in the earth observation domain, and also a few pretext tasks which were more proposed in the context of the earth observation itself. We will continue our discussion on self-supervised learning in the next lecture. Thank you.